Looking at sample problem 2-12, we're going to solve that problem as shown here. So basically it's a cannon with a projectile in a critically damped system. So the question goes, the schematic diagram of a large cannon is shown on the figure. When the gun is fired, the high pressure gases accelerate the projectile inside the barrel to a very high velocity. The reaction force pushes the gun barrel in the direction opposite to that of the projectile. Since it is desirable to bring the gun barrel to rest in the shortest time without oscillation, it is made to translate backward against a critically damped spring damper system called the recoil mechanism. In a particular case, the gun barrel and the recoil mechanism have a mass of 500 kilograms with a recoil spring stiffness of 10,000 newtons per meter. The gun recoils 0.4 meters upon firing. We are looking for the critical damping coefficient of the damper, initial recoil velocity of the gun, and the time taken by the gun to return to the position 0.1 meters from its initial position. Here are the roots, the governing equation, and the constants in that equation, and there's a quick diagram of the cannon. So here's a summary of the problem again. We have 500 kilogram mass, we have a 10,000 newton meter spring, recoil 0.4 meters, looking for the critical damping, the initial velocity, and the delta t to return to the 0.1 meter position. So just to describe exactly again what's happening, it's a terrible graph. Anyway, I think you figure it out. Tx. It's basically the cannon sitting here. The gun goes off, it goes up to a critical, goes to a peak displacement right in and around here, and then it asymptotically returns to zero displacement. We are trying to find the equation, or we know the equation that describes this motion, but we're trying to solve for some parameters around it. Most notably the initial velocity or the slope of the curve right in there. Okay, so what are the governing equations of motion? X at t, this is for critically damped, equals c1 plus c2t, bracket, e to the negative omega nt. Okay, where c1 equals x naught, and c2 equals x naught dot plus omega n x naught. Okay, so let's just draw a line across here. We're going to look at cc, critical damping coefficient. Okay, so we know c is equal to 2 root k over m. Nope. 2 root km, which should also be written as 2m omega n. Okay, what does omega n equal? Omega n equals square root k over m equals the square root of 10,000 over 500 equals 4.47471 rad per second. Now to solve for cc, 2 bracket 500 kilograms bracket 4.4721 rad per second equals 4472.1 Newton seconds per meter. So looking at this the equation of motion up here, if you think about it, we know x naught equals 0 to start. Really we're looking for this parameter here. We also know that at this point right here, velocity equals 0. Velocity is the first derivative of x of t. That's a terrible x. Okay, so if we can set the derivative of x of t equal to 0 and solve for t1, or solve for t, then we can go back to this equation and try to solve for this parameter right here, x naught. Okay, so let me just draw a line across here. Okay, so again, x at t equals C1 plus C2t e to the negative omega n t. Okay, so x dot equals negative omega n C1 plus C2t e to the negative omega n t plus C2 e to the negative omega n t. And we're going to set that equal to 0, and then we're going to solve for t. Let me just move this down here. Okay. Now, we can move this term over here, and then that drops a negative. We should be able to cross out the e exponents, and then that'll simplify our equation a little bit. So we're going to go C2 e to the negative omega nt equals omega n C1 plus C2t e to the negative omega nt. So those two terms cross out. Okay, so we are left with, and then I'm going to move the C2 omega n over, sorry, the omega n, this term right here, over here. So C2 over omega n equals C1 plus C2t. And we're looking to solve for t. Okay, so we're going to say C2t equals C2 over omega n minus C1. So now we can move the C2 over here. So t is equal to C2 over C2 omega n minus C1 over C2. So obviously those C2s cross out. And recall that C1 is equal to x naught. And x naught, right here, in this situation here, is equal to 0. So we are left with equals 1 over omega n. So this is the time when the velocity becomes 0. Okay, and that's when we get our maximum displacement. And that will allow us to go back to this equation here and solve, which we know will be equal to 0.4 meters, and solve for the initial velocity, this term right here. Sorry, this term right here. Okay, so going back down here. So we know, I'm just going to put a line across here, that t equals 1 over omega n, and x equals 0.4 meters at this time here. T equals 1 over omega n. So going into our equation, x at 1 over omega n equals C2 t e to the negative omega nt. So now let's substitute C2 1 over omega n e negative omega n 1 over omega n. Those cross out. Equals C2 over omega n e. And this is equal to 0.4. But what is C2 equal to? Let me just scroll up here. C2 is equal to x naught, this term right here. So we plus omega n x naught. So x naught is equal to 0, and then we need to figure out sub inner x naught, our initial velocity. So it equals x naught dot over omega n e, where x naught dot equals 0.4 e omega n equals 0.4 2.72 e, whatever e is, 2.7218, or times the natural frequency, which is 4.4721. And this all equals, this equals 4.8626, 4.8626 meters per second. So that is our initial velocity, and that's how we solved for it. Okay, so the last question is, at what time does the cannon return to the 0.1 meters per second? So exit t unknown, we'll call it t2, is equal to 0.1 equals c2 t2 e to the negative omega nt. So this equals, so it equals x dot not t2 e to the negative omega nt equals 4.8626 times t2 e to the negative omega nt. I think you need to take the ln of both sides, equals ln of 4.8626 t2 plus the ln of e to the negative omega nt 2, and this equals ln of 4.8626 t plus it actually is just negative omega nt t2. And I just need to fix something here. So that's t2. And there's no real easy way to solve for that. So just say t2 is equal to 0.8258. You'll never get that on an exam, okay? This is some kind of, maybe I could do it later. Anyway, that is how you solve this problem. And hope you enjoyed yourself. Thanks for watching.